with Parareal and hyperbolic.
Thanks for this very personal introduction. I want to talk about Parareal for hyperbolic problems, and I've always said it doesn't work. And this is still my title, but then I added, or does it? And I want to start with an example from last year, which is a parabolic problem, where I explained that boundary conditions are important in that context. So here we see the solution of a heat equation. There is this domain here, time domain is here, and I solve the heat equation with Dirichlet boundary conditions that are 0 here and here, and also a 0 initial condition, and I have a sort term that heats here, 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 and here, and that's the solution you get. So you can see the heating heats the domain a little, then it cools down again because there are homogeneous boundary conditions 0. Then it heats again, it cools down, it heats again, it cools down, and so on. That's the heat equation with Dirichlet boundary conditions at the boundary. Then I solve exactly the same problem, but I put homogeneous Neumann boundary conditions. So 0 initial condition, homogeneous Neumann boundary conditions, same heating, so it heats up the domain. It heats up the domain more, it heats up the domain more. And now you see the temperature rests in the domain because Neumann boundary conditions are like full insulation. The temperature cannot go anywhere. So there's a fundamental difference between these two problems. In this problem, the equation forgets everything. The solution here does not depend if I heated 4 times before, if I have not heated at all. It's just 0 here. So that's a perfect situation for parallelization in time. I can calculate this solution even before I had looked at all this. It's 0. It's like in a room next year, you know, if the boundary conditions are known, no matter how many people sit here every day, how many times you put on the heater and turn it off, this is completely parallel in time. Whereas here you see there is stuff remaining. So the solution here will depend on if you had turned on the heater or not. But the dependence is a very simple dependence. It's basically just the constant temperature that you need to propagate. Everything else is lost in this. So this is also a favorable situation. And with this example, last year I've shown you that you can run Parareal without coarse propagator. In this case here, you can run without coarse propagator because nothing is propagating far in time. You can get a method that converges. So that was my example from last year. So I took the Parareal algorithm. I write fine as a fine propagator and coarse as a G propagator. And here I ran with Dirichlet boundary conditions. The Parareal algorithm in blue, you see the error in the iteration. And the Parareal without coarse. So I just removed these two terms. It's just solving fine in parallel, and it iterates. And you see in this example, Parareal with no coarse even converges better with this coarse propagator. The coarse was just one big backward Euler step. With Neumann boundary conditions, that does not work. If you don't have a coarse propagator, there's no contraction. And you understand why now, because this constant would have to be propagated. Without the constant, the solution cannot converge. So here it just doesn't work. So here you need a coarse propagator. And there is a short paper about this with Stefan Rave, who is in the audience, who will give the next talk that explains this. So I decided to look a bit more carefully at the mapping in Parareal that is used in this Parareal method. So I look at the mapping F. This is a mapping that takes initial data and propagates it across an interval. So this mapping is F. Here I take it from 0 to t because it doesn't depend on time. And I check what this mapping does for the unit basis vectors. So I insert all basis vectors, E1, E2, E3. I calculate the mapping. So I can calculate explicitly this mapping for the heat equation. It's a matrix, it's linear. So this gives me a matrix that describes precisely for any initial condition I can multiply the matrix with, and I get what happens at t. And I do the SVD of that matrix, singular value decomposition. And here you see the decay of the singular values of this mapping for different time intervals, t1/2, t1/4, t1/8, t1/16. So if I go long in time, t1/2, I only have 3 singular values, which are basically non-zero, and the rest is 0. Here you can see that everything is basically forgotten. There are only 3 modes, maybe a 4th mode that survives, but the scale here is logarithmic. So here I'm already at 10 to the minus 10. So virtually nothing survives in this mapping. The one that survives the best is this one. It's a 10 to the minus 2. And the rest does not. If the time interval gets shorter, more survives. More survives. And if the time interval is really short, all this here is surviving in the mapping. So this mapping can be extremely nicely compressed if time is long. And it can still be quite well compressed if time is shorter, because this is 10 to the minus 5. I need about 8 values, 8 vectors to propagate. So with a dimension 8, in this case, I can propagate the fine propagator exactly. In a mapping, there's just dimension 8. And if I'm longer in time, a mapping of dimension 1 or 2 is propagating this at an accuracy 10 to the minus 8. If you look at the Neumann case, at first it looks exactly the same. You see you have the same blue decay, red decay, yellow decay, and violet decay. But if you look more closely, there is one additional value up here. This value is 1. There is a singular value of size 1. And this one does not decay at all, which we've seen in the plot. It's the constant mode. So we can look at these modes. I can take the singular vectors in these modes. So here you see the singular vectors of the mapping. You see the first mode. This is the one that survives the longest. This is the first sign mode. And the next mode associated with the next singular value is the red mode. And the following one is the yellow mode. And then the violet mode. So with this insight and Fourier analysis, you can prove the results that I showed last time that are in this short paper, how you could get a good coarse propagator. And the best coarse propagator, in my opinion, now for parareal methods is really such a coarse propagator. You look at the mapping that you have, you get a reduced basis for that mapping, and you use this as a coarse propagator. Then you have no problem with spatial resolution, no problem with time integration. It's the best possible map for the modes that do not converge fast in your method. So that's what I would do. Here you get the Neumann case. So there is the constant mode, which is the first one you need. And then there are the cosine modes, like in a Fourier expansion, because you have homogeneous Neumann conditions. So cosine mode, next cosine mode, next cosine mode. So this was the fundamental idea, to do a reduced basis type coarse propagator. And I think this is really a very, very good approach. That's what I would recommend for any parabolic problem. Now, it's easy to use a coarse grid, to use a G with another discretization, but it's even easier to just take your fine discretization, do a randomized SVD, propagate 2, 3 modes, do a little oversampling, get a dimension 4 coarse space that costs nothing, and you get the best coarse propagator. And this is a topic you will hear more about from Stefan Rave. He has beautiful simulation. He has a lot of analysis, full analysis of the performance. He will talk about this, and there is an upcoming paper. So he will give a talk about this. Here is a review of literature that dates almost 10, even more than 10 years ago. There is a paper by Jan Hesthaven. I was in Roscoff when he presented this work. He proposed to use reduced basis methods for the coarse propagator. And I didn't think much about it, which was a big error. And the reason is because he proposed to use this almost exclusively on hyperbolic problems. And I thought parareal for hyperbolic problems just doesn't work. So it didn't make any sense to me. So I almost neglected this. This is a very interesting paper. They have like empirical interpolation. They do nonlinear problems. There's a lot of work, a lot of knowledge on reduced basis. I didn't think too much about this. There was even earlier work here, also advection dominated for more hyperbolic cases. So didn't look well enough. I looked at the Krylov parareal method. That was a motivation, Jan Hesthaven said, which is a method that uses the fine propagators as a subspace to do the coarse one that's in that subspace more accurately. It's an expensive one. I studied that one. It's too expensive with the orthogonalization. The idea goes back to Farad in an earlier paper. Now, there is related work as well, but it is different. There is a reduced model-based parareal simulation for oscillatory methods by Laura Grigori and collaborators, and we just heard in 2 interesting talks. There's underlying work by Beth Wingate. The idea here is different, and I still don't fully understand it, which you realized from my question. The idea is different from what I say here. It's more a heterogeneous multi-scale method type, homogenization method type approach. So now I want to get to hyperbolic. So I showed you here, I didn't think much about hyperbolic. So let's look at the hyperbolic problem. I take a wave equation, second order wave equation, and I do an experiment which is very similar to my heat equation experiment. So here I have the wave equation with Dirichlet boundary conditions and the same source term. It's like injecting energy. And you see a solution which is reflected at the boundaries and propagates through the domain. And then I take different boundary conditions, not Neumann, I take transparent boundary conditions. These are boundary conditions that let everything go out, nothing reflected. And now you see that looks close to my heat equation problem. You see there is a source term here. This generates waves, they go out. And there's another source term here, it generates waves, they go out. There is an average remaining, like in the Neumann heat equation case. So it's very tempting to think this one is easy for parareal. The only thing you need to propagate is a constant, like in the heat equation case. Whereas this one here looks quite nasty, because if you change this here, this is going to go through your domain. It's going to end up here. That looks much harder. Yes.
Why is an average remaining if the waves go out?
Because I put energy in here. Yeah, maybe you didn't think about absorbing boundary conditions. Often you think about an initial condition, and then the waves just go out. If you have a source in the domain, this energy is staying in the domain. There's the constant mode that remains if you have transparent boundary conditions. Yeah, maybe you didn't know. That's just something that happens in transparent boundary conditions. The energy that you put in is there. If you suck out energy, it's gone with the source term. So let's run Parareal on this. So here I have the same Parareal algorithm. I look at the convergence for different delta t, a delta t that's size 1 and a delta t that's size 1/2. And if I have Dirichlet boundary conditions, you have the typical Parareal behavior. It just doesn't work. And at iteration 6, because here I have 6 time intervals, I get the solution. And if I have cut the time interval length into half, I need like 12 iterates, and then it converges. That's a typical Parareal behavior for hyperbolic problems. It just contracts once you've iterated through. And then with the transparent boundary conditions, it's very different. So bang, it goes down, and I have my solution. But if the time interval is shorter, it does not work. So why does it not work in this case? Why does it work in this case? So it was an interval of 1.5. So if I go back, if you look, here is the interval 1. And you see data that's from this domain. If it comes from here, it will leave the domain at interval lengths 1 or more. So if my course time interval is 1 or more, it's going to work. If it's less than 1, I'm screwed, because this data is still going to hit the initial condition. That's exactly what you see in this experiment. So that's why here it works and here it doesn't. So I thought I would look at this mapping again. Let's look at the singular value decomposition. Let's look what happens. So I take my fine mapping for the wave equation. I construct the matrix. I do a singular value decomposition. This is with Dirichlet boundary conditions, and you see there's no decay. So this one I cannot compress. To make a coarse propagator here is really hard. You need to have all these modes. You need to fine grid basically to propagate this. Otherwise, not possible. And this for all time intervals, short, long, whatever you do, because these reflections, they never die. Just remain. So here is the singular values for the one with the transparent boundary conditions for different length of the time interval. So shorter than 1 is not working, which you know now because the reflections have not left the domain. Longer than 1 is working. So this is what we see. It goes immediately down. But there is something funky here. I have 2 modes, not 1. There are 2 modes. Now, you know, transparent boundary conditions are not so easy to do. At the continuous level in 1D for a wave equation, it's du dt plus du dx equals 0. So I discretize that one centered in space and time. My scheme inside is centered in space and time. It's second order. I don't know if this is exact, but it looked very much exact when I looked at these simulations. This looked very much exact to me. But now if I looked at these singular values here, I see there is a second mode remaining. So my transparent conditions at the discrete level are not exact, and there is a second mode. So these are the modes associated with the Dirichlet boundary conditions. You see, it's hell. This you cannot do on a coarse grid. There's just no way. No way you propagate this on a coarse grid. But even in the transparent, now I started to put quotes here because I discretized this. So I have my constant mode, this is good. But the other one is a highly oscillatory ±1 mode, which in the meantime, I looked in the scheme, I actually have this mode. This mode is also going. So in my coarse experiment, because I had a very smooth solution, I didn't see that. But if I had a highly oscillatory solution, this should appear. So let's put the highly oscillatory source, and it's broken. You see? No, it doesn't work anymore because I do have a coarse grid coarse propagator that was good for the constant mode, but that highly oscillatory mode it cannot get. So if you're really transparent, and if you go long enough in time, then you can do Parareal for this hyperbolic problem. It's going to work like a charm. You need a constant mode in your coarse propagator. You can do this with an SVD or a coarse grid, whatever you want. But it must be perfectly transparent. So this brings me to the second topic of my talk. Maybe in nature, these problems do not exist. Maybe this is just a mathematical abstraction, these hyperbolic problems. It's not true that there is no damping, because you saw here that the fact that there's no damping is breaking the algorithm. There's no damping. So maybe in reality, there is damping. So I take a string. So I have Dirichlet boundary conditions. I take a string here. It's like a guitar string. I pluck it and I let it go. And the model for this is usually advertised to be the second order wave equation. It's the wave equation which I've used all along. So is this a good model for the vibrating string? When I was teaching this, in my second time I taught time paralyzation in Geneva in a master's course, I thought I would just show this instead of showing the normal Gaussian wave that goes back and forth, because I thought it's a nicer example. And I was preparing my lecture the night before, and my string did not oscillate as it was supposed to. So this is what I saw. Here is a simulation. I do my wave equation. This is the string. I do the second order wave equation, centered finite differences on the CFL. The best scheme I know for that equation. So this is not damped because I have 0 parameters for the moment. You see, this is not what you see if you take a violin or a guitar and let it go. It's not looking like this, never. And it's just going on forever, you know, it's hyperbolic. That's what this equation does, and it's a D'Alembert solution. It's a discrete one you can see, so I really have a scheme, but the continuous solution would look like this as well, just no wiggles. So that looked really wrong. And I was preparing my class, so I panicked. I thought, I know what damping one puts in general on a wave equation. It's just first order damping. You put a UT term and then it damps. So I put a UT term and I looked. But then it looked like this. So that didn't look good. So where was my damping? So if you look, actually the amplitude is going down. Yeah. You see, this will stop off 6 oscillations, but that's still not my violin string. It's just wrong. And it was getting later and later, and I thought I need damping. That's depending on the frequency somehow. I need high frequency damping. So added a Laplacian with a DT term. That was just with a desperate
Start turning knobs.
So I added a Laplacian, and then I got this. And then I thought, oh, this starts to look more like a vibrating string. Because it should just be a sine function, right? It should go like this, the sine. And that makes the pitch. It's the length with the sine. And so you see, that actually does produce this. So at that point, I coded this with an explicit scheme, and it was like having stability issues. So it just took a very fine time step. It was good. This is now good implementation, second order, implicit, wherever needed. So that's more appropriate. And so I gave my lecture the next day, and I sent a message to Patrick Joly in Paris, because he had shown the simulation of the grand piano a year before, where he calculated for a grand piano every note you can play, 13 hours per note simulation time, because he had from the hammer to the vibrating string to the piano body to the 3D air and then a microphone. And he said, yeah, obviously he knew that. He had that term in the simulation, you know. So this is well known, but I discovered it desperately doing my class. So going back to this more realistic problem, This is the first order damping. R is a parameter times d dt. And this is the called viscoelastic damping, ddt of a Laplacian. This is the one that damps different frequencies differently. If you do a Fourier analysis, you get a k squared here, and then every k is damped according to the size of the frequency of the oscillation. So what does Parareal do if I put this equation now instead of the wave equation? Then the solutions change. So this is the undamped case, Dirichlet conditions. Now I forget about the transparent conditions. Dirichlet, this was the original. Here I add the first order damping, size 1, R equals 1. You see the solution changes. If I add 10, the solution starts to look like one that Parareal can deal very well with. You see, this is completely local in time now. Same sources as before. So here I can calculate the future without knowing what's happening because it's forgotten with damping. Viscoelastic damping, you need less, 0.01. This still looks harder. 0.1, this looks local. So for these, Parareal should form well. So let's look at the mapping again. This is the F-fine mapping of Parareal now for the damped case. This is the first order damping, and this is the viscoelastic damping case. It's the decay of the first singular values. And you see now they start to decay like for a heat equation. Here I need like 4 or 5 modes, more modes. But if this time window is short, it's still much harder, much harder. And viscoelastic damping has a different shape. You need more modes, but also looks like it could work for Parareal. So let's run Parareal. So here is iteration index, here is error. I have the Dirichlet case from before, which did not converge up to the 6th iteration, and then it goes down. I have the absorbing the transparent boundary condition here that we've seen before. And then I damp with R equals 1. This gives the yellow curve, not much better than the undamped case, or with gamma equals 0.01. So it's very similar. Or if I take more damping 10 or gamma 0.1, I get to this. So you see, you can make this work for the wave equation. You have enough damping, your problem is gonna, your Parareal is gonna converge. And we studied this with Thibault and Auschra. There is a short paper about this that studies this very carefully. And in particular points out to another problem that I will show. But is this damping still representing my vibrating string? The one that makes it now work better? So we can go back to my vibrating string example. And I put exactly the damping that created the second convergence curve. If we look at the vibrating string with damping R equals 10, that's the vibrating string. So here Parareal works well. but you see this not really vibrating anymore. So this is called like over damping. The string basically doesn't oscillate anymore. It's just exponentially decaying to 0. So here Parareal works very well, but not much left of the hyperbolic nature of the problem. So let's look at so this was 10, no viscoelastic damping. So let's look at the viscoelastic damping case. That worked well with Parareal, so 0.1. You see it still oscillates a tiny little bit, but also not that much. So for problems like this, Parareal works well, but it's not really hyperbolic anymore. This is too far away from the physics that you're interested in.
Banjo string.
Yeah.
Don't say anything about banjos.
So to conclude, the main message of my talk was for parabolic problems. I think one should use reduced basis techniques for the coarse propagator. You get rid of every problem you could have. It's not harder to code. It's so much lower dimensional because nothing, you need a few modes. It's going to work like a charm. For the wave equation, for the hyperbolic map, it cannot be compressed. You can reduce basis, but you need all modes. Otherwise, it's not going to work. Transparent boundary conditions are great. They make the wave equation forget everything. So you can do Parareal with a very simple coarse propagator. It's going to be good. It's going to work if the time interval is long enough. And natural damping can make Parareal work. but you need a lot of damping. So if you have tests for a hyperbolic problem, very carefully check how much damping you have before you say you have a method that works for a hyperbolic problem. And be very careful with numerical damping. For example, if you coat the string with an implicit numerical method, you get Parareal to work, but your vibration is going to look like my overdamped vibration, your solution. So look at the solution that you calculate. Look at it. Is it really hyperbolic? And you can still get the Cyan book from last year from my webpage. It's still there for download. At some point, I will have to take it off. And I just want to cite important work for hyperbolic problems because the MGrid group has done tremendous efforts to make MGrid work for hyperbolic problems. It's difficult. It's a difficult subject. There are many, many references here. It's hard to get a coarse propagator to work. But we'll have a very interesting talk with Rob Olgu later this week about this. It's really hard to make this work. Huh? From my talk, you should see this is really, really not easy. This is very, very hard. Thanks for your attention.
We have actually time for a few questions, so it doesn't want to